second to actually look at it. It's just so funny. Just take 1 second to examine it.
It's just a SpongeBob expression.
Okay.
Eyes are too
Oh, here we go. Okay. I don't really like the name of this section. It's the name that the book gives it. It should probably be the name of the next section, which we'll get to later this week. But we're going to talk about some different things today. First of all, we're going to talk about increasing and decreasing. We've talked about that. Actually, we've talked about most of this stuff already. We're just going to organize it into something that will help us put all this together into something that's functional. We're going to talk about something called the first derivative test. The first derivative test is a test using the first derivative to find extrema of a function. Hence the reason it's called the first derivative test. We're talking about something called concave up and concave down. That has to do with the shape of the curve. We're going to find the points of inflection. And then we're going to use the second derivative test. You don't have to be a rocket scientist to understand. The second derivative test uses the second derivative to test for extrema. And then last but not least, you still have time today to compliment two strangers. Again, not in a creepy way. Which in itself is genocide. Okay, here we go. Let's go back to the hill.
Extremely just means both.
Yeah, or like maximum.
Oh, so this is more. By John Michael.
Okay, so applying Rolle's theorem to this picture, what can you tell me about the red portion of that hill?
It's impossible.
Say again? It's increasing. Can I sit here? It's increasing. Very good. You're going up the hill. What can you tell me about the blue dot? It's the max. And what about the black region of the hill? Decreasing. Pretty simple, yes? So if the hill goes from increasing to decreasing, at some point along the way, you're going to hit the top of the hill. Make sense? Okay, good. We talked about that a little bit. That's pretty much the whole lesson. Unfortunately, we've got about 70 minutes of other stuff that we need to cover. Just to be fair, by the way, we could turn that into a valley. And if you're going down into a valley, you would be decreasing and then change to increasing. Okay, good. Mav, looking at that hill, what can you tell me about the tangent lines in the red region? Anything special?
They're all positive.
Okay, so as a clarification, as we get more and more in depth into this stuff, pronouns are bad. Okay, you want to stay away from things like it and them and they. Tell me what you just told me again without using it.
All of the tangent lines in the red region have a positive slope.
Well done. And piggybacking on that, what can you tell me about the tangent lines in the black region?
All of them have, all of the tangent lines.
It's not easy,
have
right?
a negative slope.
Yeah.
It's not.
Okay, good. Does everybody see that? If I draw a tangent line in the red region, it's going to be positive. If I draw a tangent in the black region, it's going to be negative. So one way to look at that blue dot being the max is that it changes from being in, so I did it now. The graph changes, or the hill changes from being increasing to decreasing. However, we can also say that the slope of the tangent line to the hill changes from being positive to negative. Both of those will work. We're going to choose one of them and run with it. Okay, everybody with me? Does that make sense? Good, then this is going to be easy peasy lemon squeezy. How do we know where a function is increasing and decreasing? Well, if we go back to what Helene and Mav told us, in that red region, the tangent lines have a positive slope. And it's increasing. Well, how do we know if it's increasing? That's where the tangent lines have a positive slope. In other words, the derivative is positive. The black region, it's decreasing. How do we know where it's decreasing? It's decreasing where the tangent line has a negative slope. In other words, the derivative is negative. And then the blue dot, we know that already, that's where the tangent line is equal to 0, also known as horizontal. Okay, so that's what we just did. If the derivative is greater than 0, the function is increasing. If the derivative is less than 0, then the function is decreasing. If it's going up, it's increasing. If it's going down, it's decreasing. Hopefully not difficult, yes? And again, I'm going to bombard you with a bunch of stuff, then I'm going to show you a way to organize this. I know you have this already in your slideshow, so I'll talk you through it. We'd like to know where that function is increasing and decreasing. It's a cubic, so you kind of have an idea what a cubic looks like. But we're going to find the critical numbers. And then we're going to test some regions. Okay, so how do we do that? We use something called a first derivative number line. Sometimes, depending on the problem, the first derivative number line will become a first derivative line segment because it starts and stops. This one's going to go on forever. This little business down here is crucial. You must label your number line. Why? 2 reasons. Number 1, we have a first derivative number line. Guess what we're going to get later? Second derivative number line. But more importantly, it tells you where to plug numbers. Because that's what we're going to end up doing. Okay, so first of all, you would find the critical numbers. The critical numbers for this function, you can calculate them, but it's not that difficult. You can trust me, they're at 0 and 1. So I put those numbers on the number line in numerical order. You would be amazed how many people put them in the number line in the wrong order. Now, are you going to screw up 0 and 1? Probably not, but you might screw up 1 and the square root of 3, or 2 and the square root of 3. Put them on the number line carefully, and then test regions. What does it mean to test regions? You did this last year when you were doing inequalities. Pick a number to the left of 0. Ben, what number would you like to the left of 0?
-2.
Okay, hold on, I'll come back to you in a second. First derivative. What is it? 3x squared minus 2 minus 3 minus 3x. So 3x times x minus 1. It will commonly be advantageous to you to factor it like this, because it makes it easier to determine if it's positive or negative. That's all I care about. I don't care about the value. Ben chose to use -2. So Tina might do negative a gabillion. It doesn't matter. That's what makes it such a great country. You have choice. So if I put -2 into the derivative, why into the derivative? Again, that's why this is here. It's telling you, put it into the derivative. If I put -2 into the derivative, is the value positive or negative? It's positive, correct. This becomes a plus. And you draw a little arrow going up like that. That's different than the way our textbook does it. The textbook does it straight up and straight down. I like this better. I'll explain why in a second. Ben, back to you. What number would you like to use between 0 and 1?
Let's just do 0.5.
0.5, beautiful. If I plug 0.5 in there, is it positive or negative? Negative. That's a positive times a negative is negative. Downward arrow. All right, Ben, last one. What number would you like to use to the right of 1?
+2.
Positive 2. You are a madman. Positive times a positive is positive. We get that. Okay? Now, common mistake that people make. When you start doing a lot of these problems, they start to follow a pattern. And what people get lazy with is they say, oh, I tested the first region as positive, so it must flip back and forth. Positive, negative, positive, negative, positive, negative. Or, the first region is negative, it must be negative, positive. That's not always the case. Okay. That little picture tells me a ton of information. First of all, what do I know? I know it's increasing from, function is increasing from negative infinity to 0 and from 1 to infinity. I know it's decreasing from 0 to 1. Yes, those are parentheses, not brackets. Because remember, we said it's increasing where the derivative is positive and it's decreasing where the derivative is negative. Okay, what's happening at 0? What kind of maximum? You and your parents are, you say friends?
Relative.
Oh, relative, okay, good. It's a friend's maximum. Yes. There's a relative max at 0. What does that tell you about 1? Relative min, right. Got a top of the hill at 0 and a valley at 1. It also, and the reason I like using arrows like that, is it kind of gives you a general shape of the curve. The curve being the original function. Our original function is a cubic, and if you look at that, you can kind of see that it follows a traditional cubic shape. Any questions so far? Pretty easy, yes? It's just a mechanical way to approach these problems and to organize the information. I don't know what just happened there, but that was cool. Okay, so we get that. Increasing, decreasing. The derivative set equals 0, found the critical numbers. That's what you put on the number line, test regions. Bingo, you're good to go. Pretty good with that. Say again? Because we don't know if it's necessarily the highest point on the graph. It's just a hill. We don't know what's the highest hill. Okay. Very little of this stuff has anything to do with absolutes. This is all going to be local / relative maximum. Problems so far? Easy, yes or no? Yeah, we're good? Okay, let's move on then. First derivative test. What does the first derivative test do? It does what we already did. Natalie told us, and I think you all believed her, that there's a maximum at 0. Yes? And you believed her that there's a min at 1. And again, by saying max and min, I'm talking about relative or local maxes and min. The first derivative test is the fancy-schmancy way of confirming that that's the case. So there's our function, and there's a picture of it. And if you look at the picture, it confirms exactly what we already knew. There's a local max at 0, and there's a local min at 1. Now why? Well, just like when we go back to the hill, it's a max because the function is increasing and then changes to decreasing. Or the slope of the tangent line is positive and then changes to negative. The opposite is true with minimums. Okay, so now I'm just rambling. So let's get this all put together into something called the first derivative test. The first derivative test simply looks at what's happening to the first derivative. If the first derivative changes from positive to negative, then we have a max. If the first derivative changes from negative to positive, then we have a min. Okay, and you shouldn't have to write this because it's on the slideshow. So I'm going to go back to our number line here. If you look at that number line at 0, the first derivative is changing from positive to negative, therefore 0 is a local max. The first derivative is changing from negative to positive, so therefore we have a min. If there's no change, something funky is happening at that point and we don't necessarily know what. That's going to be the most challenging problems, is when we need to figure out what's happening at a bizarre point. Okay? Good. So go ahead. Find the extrema on that cubic function. Find your critical numbers, put them on a number line, test regions, answer the question. Work smarter, not harder.
Can I just ask you guys what you guys get?
I would be working very smart and not very hard. At least very hard. At least not very hard.
It's really not the smartest, but
Well, I mean, what are you missing on practicing how to use your
I mean, because why else would
I
somebody
don't
be
have
saying
any on this.
1 in negative 5 thirds.
Science, I said chef.
I'm stupid. I found the critical numbers. Come on. Say my full name. Say my full name. Stupid. Critical numbers wrong. Actually, I also said I'm blanking too.
Well, how are you
Does that mean
doing
that you're the
it?
second
No,
blanking? Like,
honestly, I'm just
blanking the second?
blanking. Yes, I'm blanking.
Very good.
Although just blanking the second, blanking the second.
Is that what I said? See, does it get an? I wonder if I do that enough. I just do it so often where you get annoyed.
I think I'll get it.
I think y'all
We
get
have a
annoyed.
win, yeah. We have 2 wins.
Because I'm
I
starting to
just
accept it.
don't want it to happen.
I'm starting to accept it.
I was starting to accept it. Stopped everyone. So that's a victory in my life.
How to solve world hunger. We'll send Dom to parts of the world where it's like a really low developed area, and then Dom just goes around introducing themselves, and all of a sudden they're just excelling.
All right, problems?
Like in general. Wait, the points on the number line are
Okay, so let me talk you through this. I know you can all take a derivative of that cubic. I know you can find the critical numbers. I did just that. When I said work smarter, not harder, I was trying to hint that maybe you just want to pick up your calculator and plug and chug into the quadratic formula. However, there is something to be said for getting this function in factored form. By the way, that function in factored form is, hold please. That? Yes. Okay. Now, why is it sometimes advantageous to have it in factored form? Because when we start answering the questions like, is the sign positive or negative for the derivative in this region, it's sometimes easier to work with that. However, if you have your calculator, you just want to plug and chug into your calculator, knock yourselves out. Critical numbers. Label the number line. Which one goes to the left? 1 or negative 5 thirds? Oh, I'm so proud. Test regions. So, Dom, what number would you like to the left of negative 5 thirds?
-4.
Ooh, you madman, you. -4. If I plug -4 into the first derivative, how do I know to plug into the first derivative? That's why you did that there. Do I get a positive or negative answer? -4 here would be a negative times a negative would be positive. I hope I did that correctly. Dom, what's a smart number to pick in here?
0.
0 would be a good number. positive times the negative is negative. Now, I want you to get a little crazy on this one. Pick a number over here.
2.
Easy. Period just started. Positive times a positive is positive. Beautiful. What does that tell us? Aiko, what's that tell us about the function? What do you know?
It's just keeping negative.
There's a whole bunch of things that picture that I just drew will tell you. Give me one.
But like for 3, it's positive. So I'm just.
3 times 2 times 2.
Right. So it's let me write it on my calculator. 2 cubed plus 2 squared.
Oh, no. What are you plugging it in?
The original. Is it into the
A whole bag of cheese. Never made cheese that I didn't like. So now I'm trying to try out
I
my
did that
mom.
on my test.
Really?
And then the next week I got.
Which one?
So negative 2.
Beautiful. Relative maximum at negative 5/3.
Oh well.
Why?
So yeah, it's always. Since
I'll
it's
answer
the
that
first derivative test.
Why is there a max at negative 5/3? Well, if you look at the graph, look at the first derivative number line, the picture shows that.
Apparently not.
It's a max because the derivative is changing from positive to negative. It's a max because the function is changing from increasing to decreasing. All of those are the same responses.
These are
Okay.
the numbers means they're extreme.
Beautiful. Bethany, what else?
It has a relative
Doesn't say.
Yeah.
I was about to say.
Beautiful. For the same reasons except reverse. It's decreasing. Sorry, I said it. The function is increasing or decreasing, then increasing. The derivative changes from negative to positive. All of that tells me the same thing. Could you also tell me where that function is increasing and decreasing? Yeah. Arrow pointing up, increasing. Arrow pointing down, decreasing. Okay. Beautiful. Now, there were 3 ways that you could have convinced me that that's a relative max at negative 5/3. And that gets a little confusing. So the College Board decided we're going to narrow this down. And the method they like is the following. And they're going to require that you write a sentence. And the sentence tells you 3 things. What are we talking about? That's number 1. Is it a max or a min? Where does it happen? What's the x value? And why? And they like to use f prime changing from negative to positive or f prime changing from positive to negative. If you want to shorten that, you can. You could say a rel max occurs at x equals blah, blah, blah. Please don't do the BECUZ thing. Just write out the word because. But you could change the positive and the negative into a plus sign and a minus sign if you'd like. Because you're going to write those sentences a lot. That's your justification for how you know that those points are giving you maxes or mins.
Are you just?
Yeah, to know that I can abbreviate things like so this is what
I don't I usually just write B stuff.
like I do like B/C.
You guys know what I'm talking about? You eat too many Cheez-Its and that like levels off your teeth so they're like a flat surface.
Yeah.
Oh, good. Thought I was the only one. I mean, I'll want Cheez-It? Yeah? Who said yeah? Who said that you? Who said yeah? Dominic, you want Cheez-It?
Oh, blue protein, oh my god.
QB1. QB1. You over 3. Here, 55 seconds.
You do
Cheese is synonymous BCIA or CA?
I think it'd be CA.
CA, right? Hyphenated?
Oh, hell man.
Cheese it up. Cheese it up. All right, anyway, sorry. All right, back to this. So, like a lot of these problems, mechanics will sometimes bog you down versus the concept. So I have a feeling that most of you are okay with the idea of finding extrema. Right? Find where the derivative is positive, find where the derivative is negative, put the puzzle pieces together. In a problem like this, all of a sudden, things get real. Why? You have to take the derivative of that bad boy. Oh, go ahead. This will be good for you. Build character. Put air in your chest. Air in your chest.
It's gonna put it on my eyeballs. Yes.
Do I have to chain on the derivative?
Oh wait, no, that's one.
Oh, by the way, as a precursor, there are two ways to take the derivative of this puppy. Kelsey, say that again. One way is to multiply it out.
The distributive property.
The other way would be the product rule.
Is it easier to?
Which one you want to use is entirely up to you. Neither one is more better. That's what I said. In German, it would be Mas besser.
No, I'm gonna try and power. Yeah.
Did you catch that second cheese it?
No, it's curve. There's a curveball. There's a curveball.
First two are free. Are you having fun yet? No. Yes, you are. Sorry for the interruption. If I choose to multiply this out, what's the exponent on the second x?
4/3.
Correct.
I'm not giving up, but I'm giving up.
The numbers are like deceptively awesome.
The rule should be every single time I have to change multiple times. I have to go to the town hall multiple times. I walk out and then walk back.
Imagine I can't call you by your real name. You have to call you by
But every time I change.
the
Student formerly known.
Student parliament.
How would I? When they be negative, 1/3.
Hey, quick refresher. Critical numbers come from where the derivative is equal to 0 and where it's undefined. Uh-huh. Yeah, see what I did there? I wouldn't multiply it out, so that's going to make sure
Is that it? Is that the derivative? Do you have to simplify it?
Well, you have to factor it out. That is the derivative.
You even do after that.
Then you do the derivative test with the critical number.
No, like after you factor that out. Or how? How do you do this?
You take the smallest x.
Okay, so
Oh, I remember.
I know many of you are still working, but I'm going to skip the blue part because it's really easy. I'm kidding. I'm going to work with the red part because it is a little bit uglier. Now, some of you may have decided, oh, I'm going to distribute that 1/3 x to the negative 2/3 to the 8 and to the negative x. That's not the best way to do it. Instead, what I'm going to do is factor out a common term between the blue term and the black term. Okay, so what do they have in common? They have an x in common. Do I take the exponent of negative 2/3 or the exponent of 1/3? Negative 2/3. Always take the more negative exponent. What does that leave behind? That leaves a 1/3 times 8 minus x, and it leaves a minus x behind. Where'd the minus x come from? Because x to the 1/3 divided by x to the negative 2/3 gives us that. Okay. So, this is equal to 0, and this is equal to 0. If this is bothering you a little bit, notice that x to the negative 2/3 is the same thing as 1 over the cubic root of x squared. Does anything make that equal to 0? You can tell by the question that I asked that the answer is no. Does anything make that undefined? Yes. Which is? 0. Beautiful. Our first critical number then should be 0. This will give me another critical number. If you don't like fractions, that's okay. I don't either. 8 minus x minus 3x equals 0. What did I do? Sorry, 3x. That's better. Multiply everything by 3. Get rid of the denominator. Ooh, x equals 2. Okay, I'm good. That's the hard part. Finding the critical numbers. I'm going to need some working room here, so I'm going to get rid of the blue stuff. First derivative number line. 0 is to the left of 2. So, plug in a number. Plug in a negative number. If I plug in a negative number, well, look at, hold on. Let's make our life easier. What can you tell me about that when I start plugging numbers in? If I plug a negative number into that blue circled value, what does it give you? Positive. If I plug a positive number into that blue circled area, what do I get? Positive. So no matter what I do, this puppy is always going to be positive. So that's one less thing I need to worry about. That is positive. So now I just need to look at this mess, which we simplified it down to 8 minus 4x. If I put in a negative number there, I get a positive value. A positive times a positive is positive. What's a good number in there to choose? 1. Positive, put in a 1 there, I get a positive. That, ooh, Nice. And then plug in a positive gabillion. I would get a positive times a negative, which is negative. Okay, so a couple things just happened. Number one, we get something weird about 0. So in order to talk about that, let's get a picture. Either whip out Desmos or whip out your graphing calculator and graph the original function on your calculator so you can see what it looks like. And I'm going to go get some water to get these cheeses out of my breath.
Oh. Yeah. Wait. Bring them. Is that a gap? Bring them looks like a gap. What is this noise?
The program I use, like, I don't know.
Kind of weird, bro. Wait. I forgot how, but now you show me how to get my drinking lesson.
Oh, it's, what is it?
My drinking fountain.
Window? No.
It's format. My drinking.
What is it?
I like my footage first one.
Well, I like kind of the generic plan.
All things so true. Let's go light.
I was about to do it. I had to remember what he said.
That's what I need.
Okay, does your graph match the first derivative number line?
Yes.
Does your graph match the first derivative number line? Sam. Does it?
Yeah.
Yeah, what? Does your graph match the first derivative number line, Sam?
Yes.
Why? Okay. Looking at your picture. By the way, you should have something that looks like this. Yeah? What's happening at 0? Correct. So there is a region on your graph, depending on whether you have it graphed on Desmos and you zoomed in or you're on your calculator, there is a part of that graph that kind of appears to ride along the y-axis. Right? That's something called a vertical tangent line. We'll get to that later. Where does this happen? At 2. Correct. Okay. So yes, our first derivative number line matches the graph of the function. You won't always have a graph of the function to check it to see if it works, but it gives you an idea of, helps you check to see if it makes reasonable sense. Okay. So we know that a relative max occurs at x equals 2 because, yes, I'm writing out the word, f prime changes from positive to negative.
Wouldn't it also be an absolute max? Or you're not?
Well, you wouldn't necessarily know that.
Okay.
You know that because you looked at the picture and cheated. But we won't know that when we're doing this. This stuff is going to focus mainly on relative max and relative min. Okay, we good? So taking the derivative and finding the critical numbers, in my opinion, is the hard part of this problem. The analysis is pretty straightforward. Testing regions wasn't difficult. Recognizing that 2 is a relative max is. You want me to close the shade? Sure, that's okay.
It's all good.
Oh, you're a mad woman. No way. Okay, so concavity. That's our next step in the evolution. So let's go back to this picture, or go back to your picture. That guy. You'll notice the curve has different shapes. And the easiest way, I think, to recognize this is think about a parabola opening up or a parabola opening down. The left part of the graph to the left of the x-axis, this part, resembles a parabola opening up. That's called CU, which stands for concave up. The stuff to the right of the y-axis resembles a parabola upside down. That would be concave down. Concave up would hold water if you filled it. Concave down acts like an umbrella, would not hold water. That's very different than increasing and decreasing, because we can combine those things into different aspects of a graph. So notice that that graph is increasing from the start all the way up to that max, and is decreasing from the max onward. But the concavity changes somewhere along the way. Okay, so let's take a deep dive into what concavity is so that you can understand it. This doesn't make any sense. But the reason I included it is because it mentions this idea of the neighborhood again, and I've talked about that in the past. The neighborhood is a small portion of the graph. How small? As small as you want it to be. This might work for some of you. If the tangent line is below the graph, it's concave up. If the tangent line is above the graph, it's concave down. For me, that doesn't necessarily process very well. I think of it in a different way. So I like to look at the pictures here. The left picture is concave up. Okay, it will hold water. It looks like an upward-facing parabola. The middle picture is concave down. The tangent line is above the curve, but it's more like an umbrella. Won't hold water. And then this guy. And this guy gets a little weird. What's the concavity here in the black region? Up or down?
Down.
Concave down. What's the concavity in the red region? Concave up. That blue point right there is something special. It's where the concavity changes. That is called an inflection point. And this will pop up in a couple slides, but I wanted to show you while we're looking at the graph. The left picture is concave up the whole time. The middle picture is concave down the whole time. The right picture changes from concave down to concave up. You'll notice that happens when the tangent line is horizontal in that picture. Not a crucial point of information, just a little tidbit that pops up there. You good? How are we going to find that? Well, we could talk about it all day long about how to find that, but the easiest way is to look at the second derivative. Now we start getting into the second derivative of a function and its applications. And we're going to use it to test the concavity. Okay. Now, let's go back to this guy. We can talk about the derivative of that function and how it changes from positive to negative. Sorry, negative to positive. We could look at the middle one and talk about how it changes from positive to negative. We can then incorporate this part of the... Why is it not writing? Come on, you got this. There we go. That's weird. If the second derivative is positive, it's concave up. Parabola opening up. If the second derivative is negative, then it's concave down. but it also, we can pair those with the first derivative to get different shapes. Okay, so let's say, for instance, I have a function that has the first derivative being greater than 0 and the second derivative being greater than 0. If the first derivative is greater than 0, what does it tell you about the curve?
Increasing.
Say again?
Increasing.
It's increasing. If the second derivative is positive, then it's concave up. So this would look something like that. Increasing and concave up. And in fact, let me do that again to overemphasize it. It would look something like that. And you can see where I'm going with this. You can pair this up to be any of the multiple combinations. What if the first derivative is negative, but the second derivative is positive? What does that look like? Decreasing concave up. Decreasing concave up. And then, of course, the other two would be when the first derivative is negative and the second derivative is negative, and where the first derivative is positive and the second derivative is negative. Combining those two elements. Okay. We're going to focus now on just determining the concavity by using the second derivative. The process that we use is identical. Take the second derivative, set it equal to 0, find the critical numbers of the second derivative, slap it on a second derivative number line, and test the regions. Okay, so here we go. Where is it concave up and where is it concave down? Okay, I need f prime of x first. 3x squared plus 2x minus 5. We did this already, but now I need the second derivative. 6x plus 2. So therefore, my critical numbers for the second derivative is at negative 1/3. Okay, so again, that's the critical number of the second derivative. Just like we did with the first derivative, we're going to put it on a second derivative number line. Test some values. What's to the left of negative 1/3? I don't know, let's go negative 10. That would be negative. No arrows this time. Now we're just going to do concave down. Put in 0, positive. Concave up. Tells you the shape of the curve. And we're going to put all these puzzle pieces together in an example in a minute. Okay, problems? Again, it's just repeating the process we already did with the first derivative, except it's the second derivative, which means something different. First derivative is increasing and decreasing. Second derivative is concave up and concave down. Click, 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 click. Oh, look at that, I did it. Yep, oh, got it right. Woo! Okay. Now, for the sake of time, I'm not going to have you solve this one. But it would be the same process. This would be where you do it on your own. And this is another example of where the derivative and the second derivative is uglier than the actual concept of what you're doing here. Take the second derivative, find the critical numbers, put them on a number line, test regions, figure out where it's concave up and concave down. Okay, we'll have time to come back to this, I think, at the end, but I want to make sure I get everything covered. We're doing okay for time. So, do all that, blah, blah, blah. Okay, points of inflection. Those points where the concavity changed. That guy right there is what's called a point of inflection. When we're talking about first derivatives, we care if the first derivative goes from positive to negative or negative to positive because it means different things. In the points of inflection, we don't care. All we care about is if there's a change. Did it go CU to CD or CD to CU? That's it. So I took this graph and I broke it into chunks. Let's talk about the first chunk. Going from A to B is concave down. Okay? Looks like an umbrella, won't hold water. Going from B to C, concave up, will fill with water. And you go all the way along. So, concave down, concave up, concave down, concave up, concave up. Okay, so look at E. E becomes the first point that we see something weird happen. And what's weird there is that the concavity is not changing. It's going concave up and then continuing with concave up. We get that bizarre point there, which would commonly be called a corner or a cusp, but not a point of inflection. Okay, so let's just take a chunk of the graph. Let's look at this point, from here to here. I have two questions. What can you tell me about the derivative of that red part of the graph? And what can you tell me about the second derivative of the graph? Elsie?
The first derivative is 0, and the second derivative
Is what I lost in that last part.
I don't know. The second derivative is negative or positive.
Which one? Somebody else? Second derivative, positive or negative? Positive. Correct. Because it's concave up. What about the first derivative? You said it's equal to 0. That's not correct. What do you know about the first derivative? You say something, Luca? Why? Yep. Also known as increasing. The sign on the first derivative determines increasing or decreasing. The sign on the second derivative determines concavity up or down. Okay, let's try a different part of the graph. Let's go here. From P to Q. What do we know about the first derivative? Negative. Because? Excellent. And what do you know about the second derivative? Concave down, which would make it positive or negative? Negative. Good. And we can find points on the graph to satisfy all the other parts. Where is it increasing? Concave down. Where is it increasing? Concave up. Where is it decreasing? Concave up. Where is it decreasing? Concave down. Those are the four possibilities. And where it changes over from concavity is where we get these points of inflection. So notice on this graph we would have, get rid of this. Point of inflection here, point of inflection here, here, not there, and here. Those would all be points of inflection. And again, like I said, we don't care which way it changes. We just care that it does change. Okay. Now, when you put all those puzzle pieces together, you can imagine what kind of problem you're going to get. I'm going to give you a function. I'm going to ask you where the relative max and mins are. I'm going to ask you where it's increasing and decreasing. I'm going to ask you to tell me about the concavity, and I'm going to ask you for the points of inflection, all from one function. Take the derivative, find the relative max and mins, use the first derivative test, take the second derivative, find the points of inflection, test regions for concave up and concave down. They do get a little nasty. Questions so far? I know your brain's about to melt. Almost done. The last thing, we're going to skip this example. I'll come back to that. Well, I'll take you through it. There it is. I have the word. First derivative, second derivative. I factored the second derivative, tested some regions on there. I have critical numbers at 0 and 2. Slap those on a number line, test some intervals, and I know now where's concave up, concave down, and concave up. That means I have a point of inflection at 0. I have a point of inflection at 2, and that matches my picture. Now, how could I make this a little bit more interesting? I could have asked you for relative max and mins, going back to the first derivative, but again, we're good to go here. Last thing, this thing called the second derivative test. The second derivative test does exactly what the first derivative test is. And I'm going to actually talk you out of this because it's silly. So why am I doing it? Because you're only going to ever have to do the second derivative test when the problem specifically says use the second derivative test. What you're almost always going to do is the first derivative test, which we already talked about. Take the derivative, set it equal to 0, test regions, boom, done. As I said, the second derivative test does the same thing. It just relies on a different concept. So let's suppose I have this. I got an upside down parabola. And I know that on this upside down parabola, I've got a point up here that has a horizontal tangent line. What does that tell you about that point? And that seems like an inherently easy question, but I'm asking anyways. Say it loud. It's a maximum, correct. If you have a hill and you've got a critical number, i.e. a horizontal tangent line, it's got to be a maximum. So if, let's call this point C, if f prime of C equals 0 and f double prime of C is negative, then that implies we have a max. If it's concave down, you have a hill. The top of the hill must be a max. Now take that idea and flip it over. I have a valley. And at the bottom of that valley is a point. And that point has a tangent line that's horizontal. We'll call this, let's call this point D. F prime of D equals 0. That means it's a critical number. And F double prime of D is greater than 0. Concave up. That implies a min. Graph is down, causes a hill. Top of the hill must be a max. The graph is up, the bottom of the valley must be a min. That's what the second derivative test does. However, to make things more challenging, sometimes the second derivative test doesn't work. So you have to go back to the first derivative test. So why would I do the second derivative test that requires more work and probably will not work at some point that requires me to go back first? Why wouldn't I just say, and the answer is, I don't know. You wouldn't. You'd stay with the first derivative test. But again, some knucklehead is going to say to you, use the second derivative test to find extrema. It would look something like this. Okay. Oh, by the way, there's the second derivative test. This is the critical numbers. This is the concavity. And again, some knucklehead is going to give you a problem where they require that you use the second derivative test. So I'll show you what it looks like. F prime of x is equal to negative 15x to the fourth plus 15x squared. F double prime of x is equal to negative 60x cubed plus 30x. Okay, so I need some critical numbers here. Equals 0. That means that, let's see, factor out negative 15x squared would leave me an x squared minus 1. So my critical numbers for the first derivative would be x equals 0 and plus or minus 1. I don't know what just happened. It's listening to me. Oh. It just went Julia on me. How did we get this back? Fixed it.
Thanks.
Yeah, I'm a trained professional. Okay, so I have the work over here, but I also have it when I clicked. I have critical numbers at 0, plus or minus 1. I don't care about a first derivative number line. I don't care about any of that other stuff. All I care about now is I have some critical numbers. So I'm going to break them into 3 parts. Let's start at x equals 1. We'll do this one first. F prime of 1 equals 0. I knew that already because it's a critical number. What's f double prime of 1? Is it positive or negative? Well, you bust out your second derivative there, and if you wanted to factor it, you could. Take out a negative 30x, so that would leave me 2x squared minus 1. Plug 1 into that, I'd get a negative times a positive, which would make it negative, so this is less than 0. It's negative. The second derivative is negative. It's concave up. It's an upward-facing parabola. And a critical number is at the bottom of that upward-facing parabola. Therefore, this must be a min. Let's look at x equals negative 1. F prime of negative 1 equals 0. Knew that already because I did a critical number. What about f double prime of negative 1? Positive times a positive is positive. It's greater than 0. Concave up. Wait, I did this one is wrong, isn't it? This should be a max because it's concave down. So this is a max. This would be a min. And then lastly, at x equals 0, f prime of 0 is equal to 0. We knew that already. It's a critical number. F double prime of 0. Uh-oh. F double prime of 0 is equal to 0. Can't use the second derivative test. Why the heck did we do all this work when that doesn't work? I don't know. That's why I'm going to stay with the first derivative test unless some melonhead tells you to use the second derivative test. Now what do I do? Well, I'd have to go back to the first derivative and see what it looks like over there. It's just a different method to get the same results. Okay, so I'd have to come back here and go back to the first derivative test. Draw a number line, figure out what the sign is of the first derivative to the left and to the right of 0. See if it goes up and goes down or goes down and then goes up. I know your brains are about to melt. This is so much information in one lesson. Again, I apologize. But I think this will work out better, especially with the homework for tonight. So let me finish clicking here. Yeah, got that, great. Okay, boom, yep, no, yeah, there we go. Yep, beautiful. Just, oh, what about it? I did that already. Okay, yeah, yeah, there we go. Oh, yeah, never mind. Okay. So what I did is, even though I've showed you everything, the homework for tonight, day 29, is only the first derivative test to get you comfortable with that. I don't want you to do all the problems. When you go to download the PDF, you will see the numbers that I'd like you to do. I think it's 1 through 7 and 10 through 12. Don't do the whole worksheet. It gets tedious after a while. That will start getting you comfortable to using just the first derivative test. Then Thursday after the quiz, remember the quiz only covers 4.1 and 4.2, after the quiz then we'll have some time to dive deeper into the second derivative test. No new lesson on Thursday, just working on all of this stuff to get you more comfortable with doing this. And yes, you're going to run into problems where you have to do all of this in one problem. Find the first derivative, create a first derivative number line after you find the critical numbers. Take the second derivative, create a second derivative number line after you find the critical numbers of the second derivative. Talk about the concavity, talk about increasing and decreasing. Figure out where the relative max and mins are. The next step past that is drawing graphs. We're going to then take all that information and draw some detailed, pretty little graphs about these bizarre functions. We're not talking parabolas or cubic functions. We're talking about weird ones like I showed you before that you graphed on your calculator. You will be able to graph that without a calculator by the time we're done. Discard.